Welcome back to The Explainer. So we've all been there, right? You ask a chatbot a really tough question, and it spits back this incredibly confident, beautifully formatted answer that turns out to be completely, spectacularly wrong. It really leaves you wondering, are these large language models actually thinking, or are they just expertly mimicking thought? Well, today, we're tackling a massive, central mystery in the world of artificial intelligence. How do these models actually process and structure complex information? A fascinating new academic study has peered right inside the black box of AI reasoning, and honestly, what they found completely upends how we think about machine intelligence.
All right, real quick, here's our roadmap for today's explainer. We're going to cover the AI reasoning illusion, the rules of human communication, a very counterintuitive AI discovery, how the researchers tested this theory, and finally, the clash between human and AI objectives. Let's just dive right in.
So here's the core detective mystery we're trying to solve today. We already know that AI models can hallucinate. We know that the intermediate steps they take to solve a problem can be incredibly fragile. I mean, you change one tiny little thing in the prompt and the whole logic chain just completely collapses. So, how do we spot the real thinkers from the fakers? How do we know when an AI is genuinely reasoning its way to a solution versus when it's just generating text that looks, superficially coherent to a human eye?
To solve this, let's quickly ground ourselves. When we talk about AI reasoning today, we're primarily talking about chain of thought, or COTE. This is essentially a technique where an AI generates step-by-step rationales to break down complex problems and improve its accuracy. You've almost certainly seen this in action when an AI outputs the phrase, "let's think step by step." It is an absolutely crucial, powerful tool for getting better answers out of a model, but, as we just noted, it's also deeply flawed. To figure out exactly why this logic process breaks down, researchers decided to look somewhere pretty surprising: the rules of our own biology. That brings us to parts 1 and 2 of our roadmap, the AI reasoning illusion and the human communication rule. The baseline concept here actually relies on something called the uniform information density hypothesis. Basically, in human communication, we naturally distribute information as evenly as possible. We literally need a smooth, stable flow of information to avoid cognitive overload. Think of it like pouring water into a funnel. If you pour too fast, it just spills right over. But when AI reasoning fails, it does the exact opposite. It either wildly spikes in what researchers call a local overload, where it just bombards you with way too much unpredictable information at once, or it flatlines in global underuse, which is essentially just repeating trivial nonsense. So the researchers naturally hypothesized, hey, maybe good AI reasoning needs to be perfectly smooth and uniform, just like human speech. Well, Section 3. A counterintuitive AI discovery. Because when they actually looked at the data, that hypothesis completely shattered. The crucial point here is separating two distinct concepts. Global uniformity is an even distribution of information across an entire explanation. Think of this as the pre-paved, smooth highway of human communication. We like the whole trip to be easy and predictable. Local uniformity, on the other hand, just means having smooth, coherent transitions from one immediate step to the next, without any abrupt, confusing jumps. Well, it turns out applying our human standard of global uniformity to an artificial intelligence is a massive mistake.
What's really fascinating is the visual proof. If you track correct AI reasoning step by step, it looks absolutely nothing like a flat, smooth human conversation. The data shows it actually starts out really high and chaotic as the AI explores the problem space, and then it slowly, smoothly descends as it locks onto the correct answer. Incorrect reasoning, meanwhile, is just flat and noisy, with these sharp, jagged spikes. This proves that an AI actually requires global non-uniformity to succeed. It literally needs that initial messy phase of high-information exploration.
Now, researchers measure all this using terms like entropy and surprisal. Let's de-jargon that for a second. Think of AI reasoning like a complex mountain hike. When you first arrive at the base of the mountain to solve a problem, you have high entropy, high unexpectedness, high uncertainty. It's chaotic. You're exploring different trails, checking the map, trying to find your bearings. It is not a uniform experience at all. But as you find the right path, you transition step by step with local uniformity. You eventually find a smooth, low-entropy descent right to the final answer. The AI absolutely needs that messy, unpredictable exploration phase up front to ever get to a mathematically logical conclusion.
Okay, so does this hold up? Section 4. Testing the theory.
The researchers wanted to know if this structural pattern held true across really grueling benchmarks, not just basic math parlor tricks. So they tested open-source models like QN3 and DeepSeek against the GPQA Diamond benchmark. We're talking graduate-level biology, chemistry, and physics here.
They even threw law school admission test logical reasoning at it. The goal is to see if we're looking at a fundamental law of machine reasoning that applies regardless of the subject matter.
The results are frankly staggering. When you ask an AI to generate multiple answers, and then you solely pick the answer that has that specific structural signature, high local uniformity but low global uniformity, accuracy skyrockets. Just look at the AME math test data. The baseline accuracy of the model was 40%, but when filtered for this specific AI native reasoning structure, the accuracy jumps to 53%. That is a massive 33% relative jump in performance, effortlessly beating standard methods where the AI just picks the answer it feels most certain about.
And to reinforce our takeaway here, this works everywhere. By simply selecting the AI's internal thought process that matches that mountain hike structure, smooth local steps but uneven global exploration, they saw consistent 5 to 13% relative accuracy gains across all those diverse, non-math domains like graduate science and law. The structure of the thought dictates the quality of the answer. For developers and prompt engineers out there, this means we shouldn't just be looking at the final answer an AI gives us. We need to be looking at the structural shape of how the AI actually got there.
Which brings us to our final section, human versus AI objectives. Why do human rules actually harm AI reasoning? The researchers tested this by forcing the AI into a listener-aware communication mode. Basically, they prompted it to explain its reasoning clearly to a human rather than just solving the problem internally for itself. And when it was forced to act like a human communicator, it significantly altered its internal structure. The global variance dropped, the local transitions changed. And here's the fascinating kicker. By forcing this human-like communication style, the AI's actual problem-solving accuracy decreased. Communicative optimality and internal reasoning effectiveness optimize for two fundamentally different objectives.
As the study beautifully puts it, human communication is a normative performance. It's optimized to protect an audience from cognitive overload. But AI chain of thought reasoning, that's an internal, computation-driven exploration process. It's instrumental. It expects and desperately needs global non-uniformity to freely explore the high-entropy uncertainty of a complex problem before locking onto a smooth, mathematically sound path to the answer.
So, to wrap this all together, human communication heavily favors global uniformity to protect the listener. AI reasoning, however, thrives on phase-based problem-solving, where only local smoothness, step-by-step coherence, without wild, impossible leaps of logic, reliably indicates that genuine, coherent thought is actually taking place.
Which leaves us with a pretty provocative final thought. We spend so much time tuning AI to sound friendly and clear and perfectly human. But if forcing an AI to sound human literally makes it less capable of complex reasoning, are we evaluating the intelligence of our machines on entirely the wrong scale? To truly unlock the mind of the machine, we might just have to stop expecting it to think exactly like us. Thank you so much for joining me on this explainer, and keep questioning everything you know about artificial intelligence.